of the greatest men came to our department to deliver the guest lecture of electron and graces and circuits. So why I am saying he is the greatest man means, so just compare with the age and status of the society. So he started the career from 2002 and still now. In 2002 he completed the postgraduate, that is ME. After he joined as a lecturer in Eample Engineering College. Then in 2005 he went to Australia to do the PhD. In 2008 he completed the doctorate. Then he not going for a lecture, just he is started with the career of research and development. So still now he completed the 3 projects worth of 1 crore and 60 lakhs in Indian rupees. But in the US dollars it is nearly $1 lakh dollars. Okay. Then he published 130 journals and he published 3 books as an international authorized. And also he is a member of lifetime or senior member in IEEE. Okay, this is the profile of our guest, Dr. P. Sridhar Arjuna. Okay, I welcome you to all and deliver the guest lecture. Thank you.
Good morning. So I am Sridhar. I work as a research fellow and also I am commerce and steam faculty in many of the universities in India. And most probably this university is in top 50 in the engineering stream. So where we deal with both R&D and as well as academic side. And we have various departments, so mainly on biomedical, electrical, and also electronics. And you have multidisciplinary departments which has both in terms of electronics and as well as the biomedical. And mainly we work mainly on with respect to from electronic side and also electrical and also the biomedical. So it comes as a most of the interdisciplinary parts. So if you say, for example, any device, so if I want to design any kind of a device, so what happens here is you want to know what is the circuitry involved and how this each and every circuitry has been designed and how it is going to be get to the output. So you have both electronics and you also need what is the power required, which comes into the electrical, and also physiology, which is related to the biomedical. So what I am trying to deal in this class is basically of different kinds of amplifiers. So amplifiers which is being used in the different types of applications, which is mostly an interdisciplinary. So one is on electronics. So where you know about the amplifier. So you have seen, generally you heard that, okay, so make a sound in the amplifier so that you can amplify the signal. So this is the basic structure. So how this amplifier is being used in the various fields is what I am trying to deal here. Understand? So here I am not going to discuss more in detail of what basically on the definition or in the derivation of something. So I will just give you the basic work of each of these amplifiers. So and where it is applied. For example, in electronics, how it is applied, or how it is applied in terms of any devices, electronic devices, or circuits, or in the biomedical devices. Okay, so we will see according to the structure. That's why I have given us 3 different types of amplifiers. One is differential amplifier, instrumentation amplifier, and biopotential amplifier. So I will keep this more kind of interactive if you are able to answer the questions. So I'm trying to be like get what you can understand, and if you can stop me if you are not able to, if you have any questions. So the main thing is the differential amplifier. So what is an amplifier? So what is an amplifier? So have you studied an amplifier? So what is an amplifier? So what it does, what is the input to the amplifier? So input can be any signal. So any type of a signal, whether it is from a sensor or whether it is from any kind of input signal, whether it can be audio or video or anything. So you are trying to use that signal as an input where it is very weak. So you want to amplify that signal for driving any kind of an equipment. So you want to drive, so for example in audio signal, what you are going to do is you are going to amplify that audio signal to get it to a range where you can hear it properly. So what he did now is to increase the amplification of my voice based on the quality of my voice. He's trying to increase it. So you are amplifying that weak signal to get it a very high level of the signal, which is what a basic amplifier does. So how this is being used? So in electronics, small signal amplifiers are commonly used amplifiers in the sense that, so what is basically is done here is, so you have here as they have ability to amplify relatively small input signal. So in this case I am trying to take an example of a sensor, so which is a sensor is nothing but a photo. So what is a photo device? So photo device is nothing but any kind of a light passes through that. So I am converting that light, which is very weak signal, so into an amplifying into a sound or into a more higher for getting a brightness in the lamp, or in terms of I can change into a sound which can be converted into a speaker, which you can see listen that into the speaker. So how this is done? So you have here the basic diagram of an amplification stage, so which is your small input signal. Okay. So I have an output signal which gives you my larger output signal. So this is where I am going to design my different types of amplifiers based on the application. So what is gain? So gain is nothing but your output by input. So in this case you have a general term which is your, in this case what is your input here? I can take this as a voltage input and I is my input input. So if I want to see what is the gain, that is your voltage gain. So you are going to measure the output voltage by the input voltage. So this will tell you based on the gain or based on what output is required, you can design your gain, or based on the gain you can design what will be your output. So it depends on the system requirement. Okay, so I can go for example based on the weak signal, I can say that this has to be gain of factor of 50. So your output should be based on the factor of 50. So, but in some cases you need a particular voltage. So I don't need, I'm not worried about the gain, but I need only my signal has to be amplified a bit. So in that case I am trying to design a gain based on my output voltage. So these are all interchangeable based on what type of application is required. So we will see a particular application in this, how this amplifier has been used in different steps. So what I am trying to do here is to give you a basic details of what kind of amplifiers is being used in different applications. Understand? So here this is what I said. So we have amplified difference between the input and output signals is known as the gain of the amplifier. So basically how much an amplifier amplifies the input signal. So this is your definition. So there are three different kinds of gain. So if I want to measure the voltage gain, so you measure the input and output voltage. And if I want to measure the current gain, you are going for measuring what is the input current and the output current based on that. And also power. So that is why we call that as a power amplifier, where you are going to try to measure the quantity of each of these parameters in terms of different types of gains. So this is based on the previous and then you have a signal amplifier. This is what is based on your, I think in the first unit you have learned about your transistors, right? So these amplifiers is classified based on a circuit which is designed based on the amplifiers, on the transistors. So each of these is classified into based on the type of the signal. You are going to choose based on the configuration, and you can able to classify into class A, B. So class A, B, C are based on the efficiency of that particular classifier, and also the frequency of operation. So if I want to work in the audio frequencies, So if my signal is small, and what type of configuration I am going to use. So this is what each of these classified your amplifier. The general amplifier is being classified. Okay. So here, based on the classification, so we have here the direct current, because it means that you want to listen current amplifier here, and the frequency is based on the sound, so whichever sound you want to decide. And the radio frequency is for communication. So you know that radio frequency is used for communication. So based on that, you can decide what kind of amplifier you need to boost up the signal for transmission. So these are all different types of frequencies. Based on the frequency of operations, you can able to design what type of amplifier is required. So I'm going straight into the differential amplifier here. So based on the signal, so why differential amplifier? So you can say that I have an amplifier, I'm sending a signal, I can amplify it. So why you are using a differential amplifier? So here, for example, if I have a signal, so you want amplification is done based on your what type of weak signal you get. So why we use a differential is based on, this is for example two different types of sensors, two sensors in a body. So for example you have, it can be a temperature sensor, it can be any kind of a sensor. So in terms of, I talk in terms of the biomedical because I have been working in that range. So if I talk about sensor, it can be any type of sensor you can take, for example. So if I am placing two different types of sensor, so what happens, this sensor gives me same kind of a sensor. So this gives me a potential and this sensor gives me a potential. For example, the output of that sensor. So if these two, what happens here is I want to get rid of, I want to find what is the difference in that particular two sensor outputs. So if I want to do that, what happens, for example, the output of these sensor, the difference between sensor will be very weak. So you want to amplify that particular type of signal. So in order to do that, so we have generated, for example, in terms of we have designed a difference amplifier. Okay, so the difference amplifier is based on the sensor input. So it can be any type of sensor. So I talk in terms of a physiological sensor where you place a sensor in the body and find what is the temperature. So if, for example, if the two locations gives me a similar temperature, so I want to see the difference in temperature. So if this difference in temperature is very small, what I get in the output will be very difficult to identify. So in order to do that, so we are going to design, so this is a simple design which is being using a bipolar junction transistor. So here you see here, for example, in the differential amplifier, the output voltage V0, this is your V0 is given by what is AD? AD is nothing but the differential gain. So differential gain is nothing but, it's based on the difference of this voltage. So what is gain? So gain is nothing but output by input. So V0 by, so here input is your difference. So V1 minus V2. So if in this case, if my V2, one of the voltage or one of this is very zero, if one of the sensor voltage is zero, what will happen? My output voltage will purely depend on V1, which is your other voltage. So if this is your V1, and if my V1 is 0, it will be depend on V2. So why this is a minus? Why it is minus? Because if I substitute here, you get an output as a minus. So this is the reason. One, if the V1 is called as your non-inverting input, so whatever input voltage I give here, your output will be non-inverting in the sense that you will get in positive. Okay? So if my positive voltage, even if I give positive voltage V2 here, due to this difference in the voltage, what will happen? Your output voltage will be negative, which is termed as your inverting input. So this is the concept. You are going to use it in all of the amplifiers. So which is in terms of whether you go for operational amplifier or instrumentation amplifier. So this is what we are going to see. So here you can see this is a normal amplifier. So what is the three junctions here? Base, emitter and collector. So you are going to get the same. So this part is one of the amplifier and this part is your other. So this becomes your balancing resistor. So based on this, so what we are talking about difference. What is your common signal here? V. What is the common signal? So what will be your common signal here? So you are finding a difference here. So common mode signal is drives both the inputs and the amplifier equal. So common mode in the sense that if, for example, so what will happen if there is, you are finding the difference in between V1 minus V2. So you have a signal there. So if there is a noise in each of these in the sensor input. So what will be common in both the input? So what will be common in both the input? Your noise or interference will be common in both the input. So here in this case, your common mode signal is drives both the inputs of the differential amplifier equally. So it means that both in different types of sensors, if it is an actual sensor input based on the condition of the body or based on the condition where you place, your sensor output will change. But if there is a noise in both the sensors, what will happen? Your noise will remain the same. So which actually drives it both equal in the sense that the characteristics of that particular noise will be same in these both sensors. So in order to avoid this one, so this can be due to, it can be anything. If a differential amplifier, so a lot of electromagnetic interference. So EMI is one of the biggest cause in any kind of a circuit design. Okay, so interference is between the components, between the devices and within the devices. You have lots of interferences. So these interferences is called picks up unwanted interference voltage. So if both the transistor are matched, what happens? Your balanced output will be theoretically zero. But it is not actually the case, because if it is matched in the sense that I am saying if both the transistors are matched, it means your both sensors are giving the same output. So what happens? Theoretically it becomes zero. But it is not the case, because you are going to have a little bit of noise which can drive both these inputs based on your sensor what you are attaching to that particular. So this gives you, so what happens, this is the important characteristics of the differential amplifier. It discriminates because you are finding the difference. So whatever is common in that particular sensor will be removed. So you are finding that as a So how to identify this? So in practical differential amplifier, the output depends only on the differential, but also upon the common mode signal. So which is your common mode signal here. So common mode, I can say that this is an average of the two signals, because average is V1 by V2. For example, if I am considering this as a two sensors is being connected, so your common mode is your V1 by V2. So this is what. So V1 by V2 is half, and then when you are trying to identify the output voltage, so this is your output voltage V0. So V0 is based on, if I have, that can be represented as A1 plus V1, A1 into V1 plus A2 into V2. So this is based on the amplification at that particular voltage V1 and the amplification at the particular voltage V2. So substituting this, you can able to write. So here you see that V1 is nothing but the voltage based on this condition. You can write what is V1. So we are finalizing the voltage gain for the different signal is AD and for the common mode signal is AC. So your output voltage will be depending on your difference voltage into the gain and the common signal in the gain. So if the difference is in the common mode, so this is what happens, you are going to reject this signal. So you want to reject this signal so that you avoid the interference in this case. So in some cases you may use the common signal. Okay, that is different. But for this particular reason, application, you are going to identify or you are going to remove this common signal in order to avoid the interference. Okay. So in order to do that, there is a ratio which is a term called common mode rejection ratio. So whether you have studied, I'm not sure. So this is pure because you talk about only in terms of when it comes to an amplifier. So common mode rejection ratio. So this is nothing but the ability of an amplifier to reject the common mode signals. So the ability of an amplifier to reject the common mode signaling. So this is the ratio of your differential gain to the common mode gain. So what happens if your common mode gain is very high? What happens if the common mode gain is very high? What happens to your CMRR? Less. So what we have to do? So in order to reject this, what should be your so if you want the rejection ratio to be high or low? The rejection ratio should be low or high? Low. So if it is low, then what will happen? This common mode will be high. So if it is amplifies, its gain is very high, then your noise gain is very high. So you are having a gain which is more than your differential output. So increasing the noise gain. So this should be directly proportional to your, so you are trying to avoid this gain. Okay, you are making it very less to make sure that you are avoiding the common mode, you are rejecting this common mode signal by your CM. So any amplifier you take, for example, in a device, there will be a specification which talks about CMRR, what is the rate of that particular amplifier. It means that it tells you how much this amplifier can reject this common mode ratio. So this is one of the important specification of any amplifier which will reduce in terms of rejecting this common mode. Here common mode is nothing but a common signal which is affecting the output of your any kind of a sensor. Okay, so I'm talking in terms of sensor because it's an application where you are trying to find avoiding any kind of other interferences. So if you go into any kind of a transistor amplifier or in an amplifier system, your specification tells that you have to check for what is your CMRR. Based on that, you have to decide whether to use it in particular application. Okay, so we saw a differential amplifier. So this is based on the previous structure of your transistor. So using a transistor, you have designed. So this is the advent of your electronics. So when the electronics technology was coming up, so this particular type of whatever your BJT is being conceived into a small amplifying device which is called as your operational amplifier. So you can use this as so the basic structure inside is a differential amplifier. So basic structure inside an op-amp is a differential amplifier. So you can see that this is your inverting. So we saw that inverting input previously and non-inverting input. So you want to connect, so based on this, you can be able to design any kind of operation. You can do some, most of the mathematical operations using the design, using these operational amplifiers. That is the name, is termed as operational amplifier. So you can use that if I want to add two voltages. So how you can design, instead of using a big, using a transistor, so now it has been packaged into a differential amplifier which is termed as your operational amplifier. So we will see some of the example. So here it is the same, basically a 3-terminal device. So you have inverting, non-inverting, and this is your output. And you have here the supply voltage which can range from 9 volts to 15 volts based on the operation. So non-inverting is always termed as your plus, so which means that what will be your output? Here if I provide an input to this non-inverting, what will be your output? Whether it will be positive or negative? Whether it's positive or negative? So here I am not giving anything. So if I am giving the input here, so this is being grounded. So your V1 is nothing. So you are providing an input to V2. So what will be your output? So what is your output here? V out is nothing but V1 minus V2. That's what we are seeing. The structure here is your differential amplifier. So inside is your differential amplifier. So if V2 is positive, then I am going to get here positive. So here what will happen? This is my inverting input. So this is basically you are providing positive voltage, and I take a difference, it gets your negative. So this is why the term is called inverting. So inverting and non-inverting. So this is what, and basically we use two inputs here in order to that. And whatever I have seen here, the differential amplifier which I showed it to you, whether it is an open loop or closed loop. Do you know about what is open loop and closed loop? No? So open loop is a system which has, whether it has a feedback or not. The system is in, so here whether it is an open loop or closed loop. Open loop? How it is open loop? So you have input, so your output is depends on your input. So your input, you are just giving an output and this gives your output. Sorry, you are giving an input and this gives your output here. So your input will not vary with respect to whatever is happening in your output. Okay, so since it is an open loop, so whatever you give input, it gives you as an output. So if I provide a feedback to the system, if I provide a feedback to this system in the sense that your output, the change in output will affect your input. So that is termed as your. So can you give an example of a closed loop? General example. Any automatic system. So for example, you have a water level indicator or water level indicator system. So what it does in water level indicator, so you have seen that any kind of a water level system, so it gives you the level of water, and based on that your pump will be switching on. So if I keep as an open loop, what happens? So it will check the water level, the sensor will give you the output, that's it. So because it's not going to the wall. So if the water level is less, what happens? Sensor will just tell you that water level is less, and someone has to go and open. So it becomes like an open loop. So there is a intervention. So if I want to give the same output give that as a control signal to a particular wall, what happens? So this becomes like a feedback. So you are providing it to the system, which is an automatic. So based on the particular level of the water, what happens? Automatically your wall will open and then it starts to fill up the tank. So once it reaches a point, it will again the output goes from the sensor, it stops. So that is complete as a closed loop system. So here most of these operational amplifier has negative feedback or positive feedback. So if I give a feedback from output to the terminal, it's a positive one. If I give from here to here, it's your negative feedback. Understand? It's a simple. So you have a differential amplifier. So I'm giving if I'm not giving any feedback, it becomes an open loop. So if I give a feedback, I'll give you an example to show you how it works. So this is your feedback. If I give a big feedback, then you design that gain is called as your closed loop gain. So if it is an open loop, then it is called as an open loop because you will be in the gain, whatever you are seeing now, you are only using the gain is V0 by Vn. Okay, so if I use a feedback, then your gain will be different because your feedback resistor or whatever feedback you are given will be acting upon your gain. Okay, so that will affect your complete system. So this is what is termed as your inverting and non-inverting, and this is a simple operational amplifier. So here, so we have different types of op-amps. So this is a simple example. I'm not going to go for derivation here. I'm just showing you. So here, what happens? This is my. So now, what is this RF? What is this RF? Forward resistance. So you are still in the BJT mode. Okay. So BJT you have RF, which is about it's forward resistance. But what happens also, you can say that it's your feedback. Okay, in this case, I am talking about in terms of you can stop this as a feedback. So you are providing an output here, and it goes back to this system, and this is your input resistance. So here what I am giving here is V1 is 0. So V1 is 0. So I am giving only one input to the inverting amplifier. So I am giving only one input to the inverting amplifier. So what will be my gain? So V out by V in. So if I derive this, I can get, because why it is minus? Why it is minus is because it's inverting. So inverting minus R out by, so there is a derivation. I'm just writing the final one. So here V out by V in. I don't want to fully go mathematical terms. So here it is minus R out by R. So it means that this is your closed loop gain. So which involves this resistance as well with respect to this. So now I can find, so what happens, I can adjust the gain only using these two resistors. So I can adjust the gain. So I'm not worried about how much is the voltage I want, what is the input voltage. So I want a gain of, for example, 50. So I can, based on this, based on the gain, I can able to assume this resistance, which is, for example, any resistance, and I can find what is this resistance. Or I can assume this resistance, and I can find what is this resistance based on the gain. So here you get a non-inverting. So what is an example? So this is an example here. So this is your simple trans-resistant amplifier. What happens? What is a photo device? What is a photo device? Light sensing device. So it senses the light and gives you what is the output. So based on the light, it provides you the current will change. So based on the current, if I use a light resistance here, which is your trans resistance, which is called as a trans impedance amplifier, this can be used as a current to voltage converter. So what is the output here? The photo device gives you a current. So based on this current, so I can able to write, because this is a non-inverting one, sorry, inverting amplifier, based on this resistance, what is V0? V0 is I into R. So here I am giving only one input here. Based on this, I can basically give input as a current based on the photo device, and then output will be my voltage. So this can be used as a current to voltage. So it means that it can be used as a low power. Why I am saying that, you can say I can use any other current to voltage. So if there is a low power application to convert by a photodiode into a usable voltage. So for example, you have a photodiode. I know that the current is coming. I want to use this photodiode to control something else. So I can convert this current based on the light, brightness and everything. So the voltage goes in. Based on the light condition, you can give voltage to drive some other circuit. So you can go for driving a control or driving a motor based on the light. Or you can say that when the light comes in, you can stop the traffic or something like that. So based on that, you can say it uses, so here the input will be very low power. This photodiode will take only very small voltage. So here this is what based on your system. So this is an example. This is an example where you can use. So this is basically an amplifier, which is an operational amplifier, which can be used for different kind of operations. So now you see here, so what is this resistance? This is, I am providing a positive feedback. So this is in this side where I am providing a feedback to this input, because this input is your negative, sorry, this is your negative feedback, this is your negative terminal. So this is the same circuit of previous one. So it's only interchange. But the input, what you give here is your, in the positive side, so which is based on, so your output will change based on your RF by R. Okay, so what is your input? Input you are giving in positive side, so you get here as a positive one. So this is your voltage gain, which is your non-inverting amplifier. So based on your application, you can able to design whether you need non-inverting or inverting amplifiers. So where it is used, the inverting one, sorry, the non-inverting one, so which is your input here. So I give a feedback. I want an output. So in this case, for example, if my RF and RM are equal in the sense it is very high. So what will be my, so not equal in the sense that one of each is your 0 and one is your infinity. So it means that it gives me a gain of high infinity So whatever voltage it comes here, it goes back to this point. So what is your gain here? So this I am trying to avoid. So if my RF is 0, what happens? So my RF is 0, what happens? What is your gain? Gain is 1. So that is what, so this is what is termed as your unity gain. So in the sense that whatever input voltage you are providing, you are going to get. So can I use this in the inverting amplifier? Can I give the same input here and find what is your, will you get the same voltage follower circuit? No, because your gain will change. So in this case, the gain will change and also your output will be in negative because it's an inverting amplifier. So here you are providing, this is your voltage follower circuit. So this is a simple circuit to check whether your amplifier is working or not, because you are providing the voltage and you are checking whether you are getting the same voltage. So whenever you are going to design any kind of a system or a circuit using an op-amp, it is important to find whether your chip is working or not. How do you do it? So if you are going to design, so you know that your technician is going to give it to you. But how do you know that whether it is working or not? So only when you, after connecting the whole circuit, you will come to know that whether it is going to give you an output or not. So before doing that, it is important you can do a simple voltage follower circuit to see that whether whatever input voltage you are providing, whether you are getting an output voltage. Then you go for designing your whole circuit for your purpose. Okay, so now this is another example. So I said that operation amplifier is going to be used as any kind of mathematical operation. So this is one term, it's called summing amplifier. So summing amplifier is nothing but I am going to give. So here you see that all examples I am giving you in one particular input. So we will see that how if I give two inputs simultaneously what will happen. So in this case I am giving one of the input as 0 and here I am going to sum. So I want to sum this voltage in condition. For example, if I have different sensors coming out, so I will give you an example here. Sensor 1 has particular voltage 2, 3. So I want to use these 3 voltages to drive another circuit. Okay, output of these 3 sensors has to provide a voltage, and this voltage I have to use it to drive another circuit which can be anything, like to run a motor or something like that. So I have low power devices or sensors. Based on the sensor, it gives me a very small voltage. So based on this voltage levels, I want to use these different types of sensors, whatever is being connected. So if I sum up these one, I know that I will get more voltage which can be used to drive any kind of motors or devices. So in order to do this, you can use an operation amplifier. So you are going to provide V1, V2, V3 is your voltage. So you can give any number of voltage. So your gain is based on the RF by Rn. So what is your voltage? This is you are going to add the voltages V1 plus V2 plus V3 because this case is 0. So another voltage is always 0. So assuming that if it is 0, so what happens? So you are going to have only this voltage, so which will be the summation of this. Okay? So to understand this, I want you to find out how much voltage will be here for your output. Don't just add this. So what will be your voltage? The previous case, so you have V1, V2, V3. So V1, V2 is not just a summation. So you have what happens here? You have the gain as well. So gain and the summation amplifier. So what will be your output voltage? So because this is an amplifier, you are going to add this small voltages to give you a high level of voltage to drive any kind of a circuit. So what will happen here? So this is your actual voltage, which is RF, which is V1 by R1, so V2 by R3, because your R input in a general case, this is your general input where Rn is same. In some cases your R will be different, right? So what will be your, so to make you not sleep, so I am giving you a problem. So can you give me an answer for this? what will be your output voltage for this summing amplifier. So you have here R1, R2 is different. So R1, R2 is different, and your voltage is different. Because most of the people, you just see the voltage because it's a summing amplifier. What you do is 5 plus 2, 7 millivolt. That's what you say. But actually it's different. So you need to have, this is not your, because since it uses, the summing amplifier uses the actual voltage gain to compute, because your P out is depends on your gain of this amplifier. So your P out is nothing but, where it is, this is your minus, it's your inverting. So V out is equal to RF by RF into V1 by R1 plus V2 by R2. Kilovolt. V out is the voltage. You are giving millivolt, it's going to kilovolt. Are you sure? Kilo or milli? Millivolt. Kilovolt means your talking system will be, you are talking in terms of kilovolt transformer or something. So this is based on, what's the answer? 45 millivolts. So output of the voltage is about minus 45 because it is your inverting amplifier, minus 45 millivolts, and it's negative as it is an inverting amplifier. So here, if you are looking into just a summing amplifier, it uses, because now you can see the sensor input is very small. Okay, so here even it is very small. So I am combining this sensor input and I am getting out this much voltage, which is being increased from a particular gain based on this gain. Understand? So this is enough for me to drive any kind of a device. But with only with these two voltages, I won't be able to do that. Okay, so you are going to design a circuit based on your application. If I want to increase or so that different type of sensors are used, because currently you have many sensors. If you take any device, for example, even in this air condition, you have a sensor which is your temperature sensor. So based on your temperature, you can able to automate, you can able to reduce. So based on your input, based on the room temperature, it tries to maintain in that 25 degrees. Why you are not able to get cold or off? Because it tries to maintain that 25 degrees based on the room. If room temperature increases, this will increase the output. So how it is being increased? Because temperature sensor will give you only a minimal voltage. So you have a circuitry where you can, this is a simple example, so where you can able to, based on different sensors, I can able to drive any kind of a device. So if I want to have very low power devices. Similarly, integrator. So I can use a mathematical function. So this is a bit more complex system, which is an integrator. So integrator, why I am using a C? Because C capacitor is nothing but it's a, what happens here is you performs a mathematical operation. The output responds to the input voltage over time. Because the capacitor, what happens over time, charges and discharges. So this is a variable. Your I capacitance of the current, the current capacitance of the current is nothing but change in the voltage with respect to time. So this is the concept. So if I want to find, because that is why you are going to use integrate. So if I want to do integration, it means that you are finding the differentiation opposite is your integration. So you are going to use these two formations, which is your RC network. So you are finding the resistance and C network, so which gives you proportion to the integrator of the input voltage. So why I am using capacitor is nothing but because your capacitor charges with respect to time, charges and discharges. So if there is a variable voltage with respect to time, so your integration is also what? Integration is also the change in any kind of quantity with respect to time. So you are going to use this concept in particularly for developing an integrator. So this can be used in any kind of applications which requires a mathematical operation of the integrator. So instead of doing in the software, you are doing in a hardware. So in the hardware structure, you are going to integrate the system and integrate that particular value and provide it for your any kind of an application. So we saw what is a differential amplifier, but we didn't use it for we didn't use it in terms of an op-amp. We saw in the BJT. So the previous one, what is the difference is you gave input only to one of the terminal, whether it is inverting or non-inverting. So other terminal was 0. So the actual differential amplifier using op-amp is you require two inputs in both non-inverting and inverting terminals. So you are providing V1 and V2 in this is inverting and non-inverting. So you have a feedback loop. So this is basically your output will be based on V2 minus V1. So this your gain is based on R3 by R2. So your output gain is based on R3. Your output will be based on your input. So differential amplifier amplifies the voltage difference. So whatever this voltage difference is here will be amplified. So for example, if I get two sensor input, if I want to check whether these two sensors are giving me similar output or a different output, so you can able to see that the difference in the output is what I get here. If the difference is more, your output voltage will be more. If I want to find, for example, I have two sensors, similar temperature sensors. Okay, so I am placing it in one corner of the room and other corner of the room. So if I want to check whether both the sensors are giving me a particular temperature, so how we can automate. So if I get a 0 here, what will happen? So what is your inference? So it will give you a same temperature. You won't get exact. So if the difference is 0, so even if it is a gain, what will happen? 0. It will be 0. So ideally speaking, it will be close to 0. It cannot be exactly 0 always. So there will be some kind of an amplifier. That is what a signal. That is what we term as a common mode. So common mode is what gives you that particular signal. Even if it is subtracted, you will have a small amount of voltage. So this will be used in these kind of applications. It's a small simple applications I am saying. So if I want to find the difference between two parts of the place, so or I place whether the level of a particular table is same or not, I can use it with the sensor and find whether this level of the load or whether the load is same or whether the load is varying. So I can place any number of sensors and I can find the difference between what is happening. So this is an automated system. You can use to say that because this can be used in a software. You are going to provide an automated circuit design which will be done in the hardware itself. So from the output of whether it can be any kind of a sensor. So this is using an op-amp. Same thing you can do with BJT, and BJT has its own advantage and disadvantage. This is being packaged to give high input impedance in the sense that high voltage. So this is a simple example. So what is happening here? So what is happening here? So what is LDR? So light dependent resistor, not light. LED is light emitting diode. Okay, LDR is a light dependent resistor. Okay, so light dependent resistor is nothing but what happens here is when there is a light pass on that particular surface, it's kind of a sensor. So there is a thin film surface or resistors. When the light passes on that, the resistance will change. Okay, so the light passes on that, the resistance will change, but the change will be very small. So what here the circuit is, I want to use that light and LED. So whenever the light passes on, it's similar concept of your what you can say that as a solar panel. So what happens, solar panel, it falls on that, it stores the energy and then so previous case is your LDR. So LDR passes the voltage and gives you a voltage. So that voltage, whether you can use that voltage to light up a resistance. Sorry, the LED. So light emitting diode. So what happens if my resistance changes, what happens to the LED? So you can adjust the brightness of the LED based on the voltage. Okay. So how this is done? So it compares, this is your resistance here. So this resistance, the voltage what you get, compares with the reference voltage Y. If my voltage is higher, then it starts to glow. Okay, if my voltage of this signal is higher than the reference, it starts to, the output, you get an output. Your stage, this is what is termed as your comparator. It compares. So you have a differential amplifier, so you can use the same differential amplifier as a comparator. So you give a reference voltage, okay, and then this is your input signal. If my input signal is higher than the reference voltage, your amplifier conducts. So if it is less than, then it conducts. So if based on this resistance, I can able to switch on and off, or you can able to dim the light and everything. So this is what happens whenever a person walks. If there is a light, you can able to switch on the light. So you can use the LDR for different purposes. This is one. So you can use this and op-amp circuit as a comparator. Okay. So we will have a small break, then we will proceed with the next one. Okay. If you have any questions, just let me know.
Please assemble at 10:50.